can write the equation. Oh, I'm going to write the Fourier transform. Okay. So for one-dimensional functions, let's say you have a function f of t. Okay, how do you make a Fourier transform? Depends if you ask a physicist or a electrical engineer. It's going to be different. I'm going to write it as a physicist. So it's a decomposition in functions like this. Okay. Those are the harmonic functions. Okay, e to the I omega t. This omega, right? So you decompose in that. That is going to be a function of nu, right? So that's a Fourier transform for one dimension. So it's a decomposition in this. What is a decomposition? You build this function as a set of sinusoids, essentially. Okay. If it was an electrical engineer, you'd write, instead of this, you'd write e to the okay, so J is minus I. Okay. But there are the definitions. If you write it with omega, then you start writing 2 pi's around some point. But let's take it as like good. And then here I'm talking about images or waves. So there are 2 dimensions. So in that case, I'm going to have one more dimension. So here I'm going to have, let's say, let's call it G of X and Y. The X and Y are the coordinates, so the X, Y. And here I'm going to write EI 2 pi. And now I need to write, instead of nu, I write Fx, that's the frequency along X. X. Can you see, or is it too small? Can you see from the back? From the middle? And here, Fy, Y. And the X, dy. And this is going to be a double integral now. And it's going to be G of Fx. Okay, so what are the units of Fx and Fy?
Hertz?
No, that's the units of nu. Fx
1
and
over
Fy
length.
is 1 over x, which is distance. So it's 1 over distance. So it's, for example, lines per millimeter. Okay, it's 1 over distance. Okay, so it's frequency. So to give you what is frequency in space. So this is high frequency, low frequency. Okay? That's a frequency in space. Okay? It's sinusoids that have different periods. Okay? Look at the period here. Different period. Yes. Now, the main difference between these 2 transforms, this one and here you have 2 dimensions. The main difference is that here you can rotate things. So you can have sinusoids like this, or sinusoids like this, or like this, right? In one dimension, there's only one option, okay? So that's the main difference. So these things are represented in a plane, okay? It's called the Fourier plane. And so you can have things here or here. One delta here represents one sinusoid like that. Okay. So each point here represents one sinusoid. Okay, so I was going to talk about this, how to generate a wave in 3 dimensions. So we know how to generate, or at least we know we can generate something in 2 dimensions, right? like this. We calculate this hologram, or computer-generated hologram, and we get this. In 3 dimensions, we can do something similar. The problem is it's going to be more complicated. Why? First, we don't know if it's possible. Okay? I can tell you it's possible to generate anything in one plane up to some constraints given by the resolution you can get. But in 3D, it's not always possible. So let's say I want to make a light that is like a bright, and in the next plane it's totally dark, and in the next plane it's bright again. Okay, so you can't do that because the light has to go somewhere. Only if you have counter-propagated waves you can do that. So that's an example of something you cannot do. So when you can't do something, you need to compromise and you say, okay, I'm going to approximate. Or you just say, I can do it. So what sets the conditions to this? How do we know? The constraint here is given by the wave equation. Okay. Whatever you do here, so you have light, it goes through the optical system. Still after the optical system, it's a wave. So it has to satisfy that Helmholtz equation that we saw at the beginning. So the equations are the same. So if I give you the system, you can use this Fresnel propagation and calculate what you have here. That's not a problem. But if I give you this and you want to calculate the system, it's a kind of inverse problem, it's called, or a synthesis problem. You need to calculate something, and it's not so straightforward. So, what we do, okay, so first an example to show you how this can really be done. So in this example, I tried to do exactly what I was mentioning. I tried to make a function that along the axis has light, dark, light, dark, light, dark. And it's impossible, I just told you it's impossible, but you can get it very close to that. The compromise is you have some light still here. And if you look at the cross section, this is along the propagation. If you look at images along the way, you have these side lobes. Okay, so you have side lobes, and the energy in the side lobes is the energy that generates the successive peaks. Okay, so here you have light. Here in these valleys, you have some light, but much lower. So by using these methods, you can still do something that is almost impossible. And this is like a movie of those images. So you have the hologram and you move the camera in this direction. You move the camera away and you see peaks of light appear and disappear as you propagate. Okay? So they're looking in this direction and light comes and goes. Okay? So this is to show that in principle you can do something even though it's impossible. And there are other things that you can do that are more realistic, more, let's say, easier. For example, in this case, we want to make, we know, okay, who knows what diffraction is? Okay, depends how you define diffraction. And one way is to say, okay, diffraction is that convolution. Okay, it's light propagating. But most people understand as what happens when light hits an edge. Okay? So we know that light expands as it propagates. Okay? And so you cannot have like you see this is pretty straight. Why is this so straight? There's no diffraction here. Who knows that? You see this light is about the same size here and there. How can I do that? There's no diffraction. Any guess? Okay, so this is diffraction can be understood as the uncertainty principle. Okay, so it works like this: the more you try to confine the light, the more it's going to diffract. Okay, and what happens with this laser is that it's not very confined here. It's about 5 millimeters, so that's pretty wide. But if I try to pass this through a thinner aperture. Let's see if I can cheat here. Okay. It's going to expand. Okay? If I try to pass it through a smaller aperture. So the more you try to confine, the more it tries to expand. And that's uncertainty principle and comes from the Fourier integral. In any case, what we try to do here is something that is very small and still doesn't expand. Still diffracts, because you can't, diffraction is the wave equation. But it becomes constant over some distance, z. Okay, so you have two pencils of light like this one, but it's much narrower. Okay, instead of being 4 millimeters, it's about 100 microns or less, as far as I know. So then you take different pictures and you see two spots, two spots, two spots. Okay? And we did that over some distance with this computer-generated hologram, which is just a set of pixels apertures. Okay? You can think of this, remember I told you the hologram, one way of thinking is you have so many pixels and some are going to be black, some are going to be white. You just need to choose the value. Is it black or white? Okay? And we did that so that we get this behavior. Okay? Now these when you have these beams that are almost look like non-diffracting, they're called non-diffracting beams, but it's a misnomer because there is diffraction. Okay? There is diffraction. Because after some distance, it expands. In this image it doesn't show, but there is a lot of background. Okay. So not all the energy is in these two, only less than 10% of the energy is in these two spots. Most of the energy is in the background. Okay, different types of things you could do with the light in 3 dimensions. So who knows what optical lithography is? So that's what you use to make chips, computer chips. Okay, so you project, you make a big mask, and then photo-reduce into some photosensitive material, and write a pattern. So the problem with that is normally you have a photoresist, which is thick. So if you focus, if you try to get very fine detail in that photoresist, when it hits the photoresist, it's going to expand. And then you cannot do a very small feature. Let me make a drawing here. So let's say this is the photoresist. This is a photosensitive material, and here you have some semiconductors. Okay? So you shine light. Now red. And you try to make a very small spot here. So you shine light. Okay? You made a small spot, but then it's going to expand. So here it's small, but here it's big. So it's not good. So you want a small spot over some distance. And people actually go a long ways to get this right. And essentially that's what we are doing here. Represented here. You don't want to get 3 lines, you want to get 3 planes. Okay? So thinking in 3D is important. You can also look at what is called the near field close to the surfaces. There is a lot of diffraction there. You see the structure here from grating. And this is optical tweezers, similar to what Ivan showed. Let's see if the movie works. It works here, believe me. Well, the idea is that you can use a light to move small particles. Light can exert a force on small particles. Well, it exerts a force on on me as well. So this light is making some force on me, it's just negligible relative to my mass. But if you have a very small particle in water, it's a small force is going to move it. Okay? So you can trap and move things around. Sorry for the camera man because I'm moving around. So the idea is that by shaping those lines, you can improve the force you exert on these particles. Okay. Now, the force is proportional to the gradient, to the how fast the light is changing. So you want to make fast changes in the light that you project on these particles. Okay. So here you have the particle. You want to illuminate this with something that is very sharp, and for that you also need to make holograms. Okay. Okay, who knows the difference between the light from a laser and the light from a light bulb? Okay, can you tell me?
Coherence.
Okay, more? If I don't know, I didn't understand.
All right, all the electric field lines, the peaks are lined up with the peaks and the troughs are lined up with the troughs in coherent light sources, and not necessarily for everything else.
No, they could be out of phase. Incoherence is not the same as out of phase. Right? You understand the reason, right?
Yeah, no, maybe.
So the functions we described before were e to the I omega t, so that's a perfect sinusoid. It's really boring to some extent. It's perfectly colored. There's no such thing in reality, okay? So what happens is normally, even the best laser at some point is going to have random fluctuations. Okay? So you have this wave and suddenly, boom, it made a random change in phase. Okay? But in a light bulb, those changes occur all the time, every microsecond, okay? Every nanosecond. So the light cannot recognize a sinusoid over a long time, so only over a short period of time. So all these are randomly fluctuating, changing, okay? So you can think of a wave. This is a perfect sinusoid. Okay, and now, boom, there was a change in phase, another phase. Okay? The faster this happens, it means that, or the more often it happens, it means that the light is more incoherent. Okay? So in real life, all light is partially coherent. It's somewhere in between, fully coherent and fully incoherent. So probably the light bulb is the closest to incoherent, fully incoherent light, and the laser is the closest to a fully coherent light. Now, in terms of we just talked about impulse response and Pablo earlier. So you can define a three-dimensional impulse response. So Pablo talked about a two-dimensional. You can define a three-dimensional and also shaping. But this would be the coherent. Okay, this is the coherent. If you come to the University of Colorado and take my class, you're going to learn that, or also if you read a book by Goodman, that the impulse response of the incoherent light is the modulus square of the impulse response of the coherent light. In other words, if you illuminate that imaging system or optical system with a laser, your impulse response is H, like this. If you illuminate with a light bulb, your impulse response is H squared, like this. Okay? Believe me. And that is, you can prove it in a short time with this argument of the randomness of things. Okay? So you can actually make three-dimensional responses. Okay? So you put a pinhole in 3 dimensions and get the response in 3 dimensions, something like that. Something that changes along the way. Okay, I'm going to skip that. This is a little bit about how to make these things. So we talk about computer, generated holograms, and diffractive optics. Diffractive optics normally is it's about the same. It's a different word for the same thing. It's a computer generated hologram. So these are, you can make them by lithography or laser writing. But you can also make a face mask that have a continuous relief. Okay, that's called a gray level lithography. Okay, where you can make something, a piece of glass with a continuous relief. You can use liquid crystals. Okay, to modulate the light. So with liquid crystals you can modulate amplitude, phase, polarization as well. Then there is this volume optics, which is something I'm going to talk in a minute. Before that, I want one other option that we have is trying to record with many waves. Okay, remember we talked about using 2 waves for a hologram. If you use 3 plane waves coming from different sides, you generate a periodic structure in 3 dimensions. Right? And people have found that that's useful for like filters and other functions because it's similar to what the structural color you have in the butterfly wings. The colors in the butterfly wings come from microstructures that are periodic. So what we were looking here is to make these waves modulated, so you can generate patterns that are not periodic. Okay, so let me show. So to give you an idea, instead of a periodic pattern, we want to make something periodic with a defect. So those that took solid state physics, this looks like a crystal with a defect, right? And so by interfering light, you can generate different crystal structures of light. And here you have like a vacancy, an edge dislocation, or a quasi-crystals. Those that took solid state know what I'm talking about. If you don't know what I'm talking about, you can look at the nice pictures. And appreciate the difference, that this is periodic, and there is something missing. That's a vacancy. Here, you see, this is periodic, but there is a line defect here, right? Because here I have 1, 2, 3, 4, 7, and here I have 8. So at some point, I generated another color. And this is a Penrose tile. If you look at the tile in a bathroom, okay, if they are square, it's easy to accommodate. If they have 5 sides, it's more complicated, right? You cannot make it periodic, correct? So that tiling thing, so if you look at this, it looks kind of periodic, but there's no real periodicity there, okay? So when you don't have that long-range periodicity, these structures are called quasi-crystals, and they happen in nature also, okay? And you can generate that with light. Okay, so by interference of light, you can generate different patterns that have some analogy with the solid state, with real crystals or quasi-crystals, but also have some interesting photonic properties. I'm not going to talk about that today because I'm going in a different direction. This is work we did with Ivan's group. So Ivan's student Rahul and my student Don built this experiment. So the idea is to make holographic tweezers. So essentially you have holograms to move particles around. So here you have 4 particles and you can move them around with a hologram, as I said before. And also a separate system, which here is this one, I believe. Right. This system here has a filter that allows you to localize these particles in 3-dimensional space. Okay, so you have an optical tweezer set up. Here you have an objective, and here you have the samples. And then you have another system that is used to localize particles. So you can track particles in 3D. So these are different particles that you are moving with one system and track it with the other system. Okay? So apart from having fun, this is useful for people in biophysics use this to study molecules and DNA and things like that. And Ivan uses it for liquid crystals. Here you use light fields in 3 dimensions, both in this SLM and this SLM. The SLM is a special line relator of liquid crystal. And then you can measure the forces by tracking the trajectories of the particles. So in this experiment, we put these are small microspheres in water. So we release one of these spheres and let it fall to the trap of a laser beam. The laser beam is exerting some force, so it brings it, the particle starts here, you release it, and then it goes whoop, to the center of the laser. You can think that the laser was here. And these are different, each color is a different experiment. Okay? And with this we show that you can track in 3 dimensions. This is X, Y, and Z. So the particle is not coming to the laser, it's going down and then coming to the laser. Okay? So it's attracting the particles, and the force on the particles follows the gradient of the beam. Okay, so I talk about doing shaping light. That's what I've been talking today. We have different holograms, we can shape the light, and we can come up with this distribution of light mathematically or numerically. You can play the same game in time. So you can shape a pulse. Instead of shaping a beam, you shape a pulse. So you come with a pulse. Let's say you come with a pulse to some system and you want to go out with a train of pulses. So you're shaping this pulse. And you can do that by using a pair of gratings and now a mask in this plane. So here the grating is going to spread. You know, a pulse is composed of different colors. Okay? Because it's a composition of different colors. And so that are coherently added, right? And each color now here in the grating goes a different way. You know, a grating spreads the colors, right? We know that. So blue goes here, green here, red here. And now here you stop, you put some mask that is going to stop some of these colors and let some other colors go through. And that's how you shape the spectrum. And then you combine back again here and you can get a train of pulses. So that way you can shape pulses. But now what we were looking into a few years ago was, can we, with a kind of diffractive element or a hologram, shape play the same game? You come with a plane, wave, a pulse, and then you shape and make multiple pulses. Now these pulses have to be very, very short. Okay? Because what is going on here, you're playing with the delays on these very thin optical elements, and so those delays are very short, so you need to have a very broadband pulse, or in other words, a short pulse. So here, this simulation shows the focusing of the pulse through a lens. So what you're going to see is how, if you could, which you can, see the pulse going through the focal region when it's focused by a lens. Okay? So this is a very short pulse. Okay? How it would look as it progresses. By the way, I use those Fresnel equations for this simulation. Okay? So you could do this. So one thing we notice is that nobody was seeing it. Why don't you tell me? I can show that. This should work. I can show it in my computer if you are interested. Sorry about that. Okay. The idea is that this pulse doesn't focus well. It's spread in space and time. And then by using these techniques, you can make this pulse focus nicer. If you want, I can show. It shows in the computer, but not on the screen. Okay. The other thing I wanted to talk is another generalization. We talk about these holograms that are two-dimensional. And now I'm going to talk about these holograms that are three-dimensional. Okay? So in general, optically recorded holograms, remember with the reference wave that is recorded optically, it can be thick or thin. Thin or thick depends, is relative to the wavelength. So this thickness has to be much larger than the wave. And computer-generated holograms can be also thin or thick, or become a volume. And that gives you some new capabilities. Okay? And you can think of this as a more general question, like we were talking about the pixels. That a hologram is just a set of pixels that you determine the value. The same you can do here in 3D. It's a piece of the material, but you control the refractive index. And making this hologram or volume optic implies determining the value of the index of refraction everywhere in space. Okay? So this is easy to say, but it's not easy to make. Now the question here is, what are the effects? Is diffraction? We were talking about what is diffraction. So clearly there is diffraction if you have small features here. You can have refraction if they are smooth variations in the index. You could have scattering if there are very small variations here. Or you can have radiation. You can think of scattering as radiation as well. So, for example, you could take one cell here and move it around, okay, like we did before. And you could take cells and move it in Z. Now because you have a volume, or you could add different layers. So you have more degrees of freedom, but also it's going to work differently. So this is actually, what is the problem? To design these things is complicated because now you need to make three-dimensional Fourier transforms to do this calculation. And then you need to fabricate these things in 3 dimensions, which is not easy. So these are the far field. This is actually something we fabricated with a laser, with a femtosecond laser in glass. And this is a reconstruction. So you eliminate this thing, which is very small. This is 10 microns. And you can see this logo in the far field. Okay? Another thing you can do is control the propagation according to the polarization. So polarization is one property of the wave, and if you come with one polarization vertical, you get one image. If you come with a different polarization, you get a different image. That's the goal. That's called polarization selective holograms. And you can do that and use this for multiple applications in sensing and interconnect. So one way of doing that is to make the same encoding we had before. Remember the cells and the windows? You shift the windows. But now each window is birefringent. Okay. So who knows what birefringence is? Yeah. Okay. So essentially it's a property meaning that the index of refraction depends on the polarization of the light. So that's you have for different polarizations you have different indices of refraction. So by controlling the orientation of what is called the principal axis, you can have another degree of freedom to encode information. I'm going to skip the equations. And so, you'll see the movie, of course. Here you have the C. If you come with one polarization, you see the C. If you come with a different polarization, you see the U. But if you come with a 45-degree polarization, you see CU. I don't know if you can see it. It's there. Okay? So this is an experiment and it coincides with the simulation. And again, we fabricated this with a laser using some interesting properties of femtosecond lasers that can generate birefringence in glass. Here is what I showed. So you focus the laser in a glass, and you can build all this structure. And if you look at it with more detail with a scanning electron microscope, you can see that there are very fine gradients with grooves in the order of 20 nanometers in width, which are essentially self-generated by the interaction of the light with the plasma. Okay, so why is there a plasma there? These are short pulses, so these short pulses are very, as I believe Ivan talked about this, very high power, instantaneous power. That generates free electrons that create a plasma eventually by multiphoton processes, and avalanche and things like that. So you generate the plasma, and then the plasma generates these structures. And here we show that you can control the birefringence by rotating two polarizers. Similar experiment to what Ivan showed.
So what are the values of birefringence you get in this case? Delta?
I don't recall the values. I recall that we could get a pi phase shift, which is what we want. Okay, we wanted to have a thickness such that you get a pi shift, or at least pi over 2. And we control that by making thicker or thinner gradients. It's probably in the papers, but sorry, I don't remember. This was a few years ago. Okay, so going back to Pablo's talk, he talked about what shift variance was. Shift variance means that if you have a point source in the projector and you look at the response here, it's going to look different than here, different than here. Okay, so I go into the field of view. Let's say I'm using these glasses. If I look through this part of the glass, it's not going to look as good as if I look through the center. Okay, that's called shift variance. If it looks all independent of the shift, it looks the same. It's shift invariant. So in some situations, we want to make something that is on purpose more variant. Okay, so you want to come with one wave, and you get in one direction, then you come with a different wave, you get in a different direction. That's called angular multiplexing. And if it's with different colors, it's called a color multiplexing. So this has so having this volume optics has advantages of efficiency first. We can also have this selectivity or shift variance, and you can encode different things in time and space. So okay, so here we go to the 3-dimensional Fourier transform. Okay, so this is our volume, and we want to design something there. Okay, so this is what we're going to do. We are going to design in Fourier space. Okay, so for the physicist, K space, if it's more comfortable. We make a 3D Fourier transform, and you get this another volume. But now the coordinates are Kx, Ky, Kz, or Fx, Fy, Fc. It's the same thing. Then, if you look in this domain at the sphere of radius 1, 2 pi over lambda, okay, that's called the Ewald sphere. Okay? This sphere has radius 2 pi over lambda, and is centered at a radius 2 pi over lambda from the origin. Okay? So here is the origin, and the center is here. And this is the direction of the incident wave. Now, if you look at the wave equation we had before, and you apply it to this case, you can see that anything has to be on the surface of this sphere. This is called the Ewell sphere. So, in order to get the diffraction pattern from this, you make a 3D Fourier transform, take the values of the sphere, and then unwrap the sphere, and you get this plane with a smiley face, which was here. If you look on this half of the sphere, you get the half. Okay. The left half of the sphere is the backscattered light. The right half is the forward scattered light. Okay. So this is expresses a scattering potential. So scattering potential is just the index square minus 1 times some constant. Okay? So you take that Fourier transform and you can calculate the far field. Now we want to design something in the far field, again the CU logo. You do that and you get the structure of the index of refraction. So after iterating or optimizing that, you get the structure. So if you illuminate this guy, you get CN, this pattern. Now what happens if you change the incident light? These spheres are going to rotate around the axis, the center here, the origin. Okay? So if the light comes this way, you get this Ewell sphere. If the light comes this way, you get this Ewell sphere. If the light comes from down, you get this Ewell sphere. So every incident direction has a different Ewell sphere. And you can play that game again, but now you can have different encoding for different wavelengths. So that's what we did here. For one incident angle, you get the C. For a different angle, you get the U. And we do that by optimization, okay? By iterating, imposing these things over time. And let me show you, I'll talk about this later. In this image, you see, if you come at 0 degree, you get the C. If you come at 15 degrees, you see the U. And these are actual experiments. These are actual experiments. This is the image of the surface of this volume optic. And these are cross sections to show that it's not periodic. It's just something that was optimized in the computer. Essentially making three-dimensional Fourier transform. And this is interesting. So if you look at the waves going through this, so now the white thing is the optical element. And a plane wave comes from the left, there's nothing here. If you look at the intensity, it's constant. As you cross this element, the waves are starting to get in modulation until you get the full modulation here. From here on, it's Fresnel propagation. Now if you come at an angle, it's the same, and you get a different pattern. So the idea is that these things depend, in order to work, you need to have the right index contrast. And this plot shows how the efficiency, that means how much energy goes into C and U, depends on the index contrast. If you have low index contrast, it doesn't work. If you have too high index contrast, it doesn't work. You need to be around the right value. And here you have the reconstructions. So it has to be around 0.01. Now if you use different colors, it's what changes is the size of the sphere, because we say that the radius of the sphere was 2 pi over lambda. Different colors have different lambda, different radii. So you get different radii. And you can put different smiley faces on each sphere and get a reconstruction that changes with the color. Okay, so with blue, you get, that's the blue we get. In blue you get C, in red you see U. And here is the actual experiment. I don't know if you can see the C here in blue and the U here in red. Okay, and this was done by illuminating with different colors. Similar thing here. The waves are generated inside the volume, and then you get this wave is going up and this one is going down. And that's what happens. So these experiments were done about a year ago, maybe a year and a half. And this volume had 64 by 64 by 64 pixels, which is very small. Right? We like to make a megapixel, voxels. We call it voxel if it's in the volume. But to show you, to give you an idea, here is the first paper on two-dimensional holograms in '67, and they had 64. Let's see, yeah, 64 square. Okay, so the problem is it's difficult to fabricate these things. We think if it's a megapixel times 1,000, it's a gigapixel. Okay? It will be very difficult to fabricate. But we are working in this direction. The same with digital holography, which is something I didn't talk. So in our case, I hope in 30 years at least, or before, we could have the gigapixel volume hologram, okay? Computer generated. Okay, so to summarize, I talk about three-dimensional optical functions. I talk a bit about optical tweezers, engineering of the point spread function in 3 dimensions. I'm going to talk in the next talks about imaging and super resolution. I talk about 3-dimensional optical elements, which we call volume optics. And these give you more degrees of freedom to get this shift variance, which is useful. We talk about controlling frequency, polarization, and you could think about controlling other properties of the wave. Okay, this is what we are going to do in the future. You can control pulses, do some hybrid functions where you control both in space and frequency things. So this could be used, for example, for something called spectral imaging, where you want to look at an image and at the same time, for each pixel, know the spectrum. There are systems that do that, but we believe that with this type of elements, you could do it in a more efficient way. Okay, that's all what I had for today. Thank you. So it's 1 in Colorado. So I finish in my 2 hours. It's 4 here. Questions? Yes.
Well, how do you fabricate these boxes?
Yes, that's a key. The way we did it is not necessarily the way you do it in the future, but we do it with a laser. So image. We tightly focus a femtosecond laser inside glass and then scan. Okay? And modulate the laser so you get you only affect this local area. The reason is because it's a femtosecond pulse, so it's very high distant power. You have some non-linear effects that modify the material. Otherwise, if you focus the light through glass, it goes through, nothing happens, right? It's transparent. The key is that we have this high power that generates some free electrons. Once you have the free electrons, they start absorbing light. That's a problem. Well, that's just depends. You know, if it's an optical instrument, you're going to destroy it because you're making marks on the glass. But if it's you can use it for good. One question.
Amplified system or just normal?
That's amplified. It's a reggae system. You can do it with a oscillator, but it's different. Different effect. So if you use a femtosecond pulses at high repetition rate and lower power, you get thermal effects. So essentially, you are melting the glass, and then when resolidifies, you get an index variation. If you have higher powers, you can make a void, or you can generate these gradients. So different powers in different materials generate different index changes in the glass. So depends on the glass and depends on the power and the repetition rate.
What have you used? 150 kilohertz? Or you want to
Okay,
use-
so this one was done at 100 kilohertz, and the power was about 1 microjoule per pulse. More questions? Okay, so thank you.